Okay, now that we have done Coulomb's law and we learned about the electric force, now we're going to learn about the electric field that was pretty much discovered by Michael Faraday, my favorite physicist. Now remember, it's the electric field that directly acts on the particles, that directly acts on the charges, all right? Since the charges are far apart, they can't exert a force on each other directly, so this one sends out an electric field, and this one over here feels that electric field. All right, so there are two main equations that deal with this. We have E equals K big Q over R squared, and we have E equals Fe over little q. Now notice we have big Q and little q. They still represent charges since it's Q, but it does matter between big Q and little q. Big Q makes and little q feels. Now what that means is this big Q here makes the electric field. This big Q makes the electric field. Big Q always makes the thing. All right, big Q is the thing that's sending out the electric field. All right, and we can figure out the electric field at any spots Q, R, and that's the distance from big Q. So big Q makes this electric field. All right, and we can find out the strength of this electric field at any distance from the from big Q. Now in our other equation over here, little q feels. Little q experiences the force. Little q is a charge that is in somebody else's electric field. So if I had to do big Q1, well, that makes electric field 1. So if this is electric field 1, let's say maybe big Q is making this electric field, then this is little q2. That is the other charge. This little q here, while it's doing its own thing, sending out its own mojo, sending out its own electric field, it is feeling a force. So when you say q feels, it is experiencing / feeling that force because it's in somebody else's electric field. All right, and we'll see examples of how to use both of these equations. All right, so the first one, I'm going to start dealing with this and just get an idea of how this generally works here. Okay. All right, in this first problem, you can see it's very similar to the first problem we did with Coulomb's law. We are trying to figure out what happens if we change just one thing. So in this problem, we are changing the spot we are talking about, all right? So we're going to take this to the same procedure. You can imagine for the first way you do it, you just plug in everything as 1. So everything that does not change stays as 1. So we're trying to figure out the E field. We know K is 9 times 10 to the 9, but that's not changed. We're going to keep that as 1. The thing that's making the electric field, we don't even know what that is, but it's not changing, so we're going to give that 1. Thing that is changing is how far. So if this is big Q here, in the first problem, we're talking about it, okay, maybe what's the electric field in this space right here. But now we want to know what happens when we go twice as far. So if this is 1 meter, what happens to the electric field? How strong is the electric field when it's 2 meters, somewhere out here? So 2 is twice as much as 1, so we put that in here, 2 squared, and we see the electric field now is 1/4 of what it originally was. Now in this problem, one thing that's different is our original one, we have the electric field is 5 newtons per coulomb, which is the SI unit for electric field. So if we go two times further away, then our new electric field is going to be 1/4 that, so it's 5 divided by 4, and that is our answer. All right, 5/4 Newton, 5/4 Newton per coulomb. All right, now in part B, they want to know what it would be 3 times further away. So we do the same thing. We're going to do E equals, well, K hasn't changed, so we'll keep that as a 1. Big Q hasn't changed, so we'll keep that as 1. But now we are 3 times further away because we're 3 meters instead of just 1. Remember, that's squared. So now E is 1/9 of what it was. Sorry, 1/9 of what it was. And if the original E is 5 newtons per coulomb. Well, now our new one is 5 divided by 9 Newton per coulomb. All right, and that would be our answer. Now we actually have an answer as opposed, so it's to the Coulomb's law problems where we just figured out what happens. Now we have actual numbers we can plug in. It's 5 ninths. And then we can do our final one, all right, where we go half a meter. So K hasn't changed, Q hasn't changed, all right, but R has changed. R is now only half of what it is, and that's gets squared. So we have 1 over 0.25, which is equal to 1 over 1/4. So E then is equal to 1 over 1 over 4, which is 4 times. All right, 4 times of what it was. So if our original was 5 newtons per coulomb, if we go half the distance, if we get closer to the thing, the electric field gets stronger. If we go further away, electric field gets weaker. So in this one, we've gone closer. We're not just a meter away, we're only half a meter away. And we see it's 4 times, not just 2 times, 4 times, because it's a square law, inverse square law. So we take 4 times 5 newton per coulomb, and we would get 20 Newton per coulomb. That would be our answer. All right, so very similar to Coulomb's law. If we get closer, the thing will get stronger. If we go further away, the thing will get weaker. But it's not a 1-to-1 ratio because in the equation it's squared. So if we go twice as far away, it's going to be 4 times less, 4 times weaker. If we go 3 times further away, it's 3 squared, which is 9 times weaker. All right, and then vice versa. If we go cut the distance in half, it's 4 times. We could cut distance in a third, then it's 9 times stronger. Closer, stronger, weaker, farther away. Okay, let's move on to the next example. Okay, in this example, we have a charge making an electric field. So we have a 9 microcoulomb charge making an electric field, sending out an electric field in the space. Or you can imagine that's like its mojo. It's sending out its mojo into space to try to, attract or repel some other charges. And we want to find how strong is that electric field 0.75 meters from that charge. So we're looking for the electric field made by the 9 microcoulomb. So that means we are talking about big Q because big Q makes the charge. All right, so we can plug in some numbers here. E is equal to K is 9 times 10 to the 9. Still the same K. Our Q is 9 microcoulombs. So that means our 9, we write down our 9, and the microcoulombs just turns in, the micro part turns into times 10 to the negative 6. All right, notice again, I did not put in a negative number there. All right, all of our numbers in in E and M stays as positive, and we do our directions at the end, which I'll show you how to do that here in a sec. And the distance from here, this is the electric field made at that spot, which is only 0.75 meters away. That gets squared. We go to our calculator, and we have an answer of 144,123 newtons per coulomb. All right. Now we have to go figure out the direction of the electric field, and that's another process. To figure out the direction of the electric field is very simple. All right. We place an imaginary proton in a spot and see what would happen. Okay, so what does that look like? Here's our big Q, all right? And our big Q is positive. This thing is sending out an electric field all over this white space here, all right? Sending out, but we want to know, what does it look like? What's the direction of that? Well, if I want to know what it looked like right here, what I would do is I would place a small positive proton there, all right? Small positive proton. Now, if I put a proton there, and there's a big positive charge here, what's going to happen? Well, we all know it's going to be repelled, so it's going to go that way. And that literally is the direction of the electric field. So what would it be right here? Well, if I put a proton there, what would the proton do here? It would get pushed that way. So that's the direction there. Down here, right, put a little proton at that spot, it would go this way. So you can see in all this space here, the electric field goes away from a positive charge. Now remember, this is just like a thought experiment. You're not literally doing this. There's the only thing in this spot here is the electric field. This is big Q making the electric field. The electric field is represented by the red lines. How do I know that's the direction? Well, it's been defined by physicists that whatever way a proton would move, would be pushed, is the direction of the electric field. So positive, they repel. That thing would be repelled this way. If I put a proton there, it would be repelled by that positive charge, and that's the direction of the electric field. Likewise, or similarly, I guess you'd say, if I have a negative charge, right, this negative charge is sending out a whole entire electric field all around. Well, how do I know what the direction of the electric field is right here at that spot? Well, same thing. Even though that's negative, right, this is big Q. This is big Q. Even though that's a negative charge, it's still giving out an electric field. And I put a positive test charge. It's always a positive test charge. And what would that proton do if it was placed right there? Well, it would want to be attracted to the negative big Q. If I put a little proton right here, what would it do? It would go that way. So therefore, that is the direction of the electric field. Whatever the direction that a proton would take, sorry, that should be a proton. Whatever direction a proton would take, that's the direction of the electric field. Down here, we would see it would go this way. So all of a sudden, if we do this everywhere, the electric field goes into, the direction of the electric field goes into a negative charge, all right? This charge is making an electric field all around it, and it's going into the charge. All right, now we go back to our original problem. It says, what is the spot above the charge? So there's our big Q, all right? And they want to know, well, we know how much it's going to be, 0.75 above. So at that spot right there, we know it's that amount, all right, at that spot. But what's the direction? Well, if I put a positive charge here, it would go down into this because our big Q is negative 9 times 9 microcoulombs. All right, so the full answer to this thing is 144,000 newtons per coulomb down. And how do we figure out the down? Well, if I put a positive charge there, it would be going into the negative Q. All right, if I reverse this and said, well, what is the electric field 0.75 meters to the right of big Q? Well, it would be over here, and that charge would go this way. So the direction would be that way, all right? We always put a positive test charge to figure out the direction of the electric field. All right, now let's move on to our final example and look how we can use that second equation that we introduced back in the beginning. Okay, once I read this final problem, we notice that we are placing a charge in an electric field, all right? We already have an electric field pointing to the right, or sorry, pointing east, all right, which I've denoted as going to the right, of 60 newtons per coulomb. And what's going to happen is they're going to place a proton in this thing, all right? They're going to put a little proton in. Now, be very, very aware of what's going on here. This proton is not making this electric field. Something else is making this electric field. I don't know what it is, and I don't care what it is, all right? But I know in this area, on this like whiteboard, there's an electric field made by some other charge going that way. Now, I know if a charge is placed in an electric field, it will feel a force. That's what actually exerts their forces on them, all right, the electric field. So this proton is going to feel a force. Now, we also just figured out that protons go in the direction of electric fields. That's literally the definition of them. Protons move with the electric field. Electrons will go the opposite way. All right, we just saw that. So now we got to figure out how much force this thing is going to feel. Well, there is our equation, all right? We know E is 60. All right, we know E is 60. We're trying to figure out the force, and we have little q, which is a proton in here. Now, what is the charge of a proton? We haven't gone over that yet. Charge of a proton, q of a proton is 1.602 times 10 to the negative 19 coulombs. All right, it's a very, very, very small amount of charge. All right, it's the smallest charge you can get. So once we see that, we can see we multiplied both sides by q. All right, both sides by q. That cancels that out. That's just simple algebra. And we get F equals 60 times little q, which is 1.602 times 10 to the negative 19. And we go to our calculator there, and we get, let's see, 1.602 exponent 19 negative times 60. It's 9.6. 9.61 times 10 to the negative 18. I'm running out of room. Newtons. And we see the direction that's going to be going that way. Now in part B, they're saying, well, what if we didn't put a proton there? What if we put an electron? What would happen? Well, it turns out that a proton and electron have the same electric charge magnitude. The charge of electron is that as well. All right, which is good because of the basic electricity units. All right, our positive and negative charges started with protons and electrons, so they have the same charge. The only difference is one's considered positive, one's considered negative. But in our equations, we plug in all positive numbers, so that in the second part, if we put an electron in there, we would still get the same answer. The only difference is an electron goes against the electric field. All right. Protons, positive charges go with an electric field. Electrons or negative charges go against the electric field. All right. And that wraps up all of our equations we need for electrostatics. We know how electric force relates to electric field. We know how to figure out the electric field something's creating, and we can figure out the forces between two charges.